just want to give you a little bit of an idea of what you're going to see and also go over those solutions to the test review that we did in class. So starting off, what you are going to see on your test. Okay. So your test is going to be probably 15-ish questions. Haven't written it yet, so go for about 15. Some will be multiple choice. You might have some numerical ones where you have to put the numerical value into Canvas. There might be some fill in the blank. There might be some matching formats, but you are going to see questions on free body diagrams. Choose the correct free body diagram. There might be little differences, so we need to make sure that we are looking at these things through a magnifying glass to make sure we got everything that we need. We'll cover both types of friction, static and kinetic. Remember, kinetic friction is moving, static friction is not. And also the max value of static friction will always be greater than the coefficient of friction for kinetic. So solving Newton's second law problems, that's going to be the big computational ones, and then know all of Newton's laws, the zeroth law, first, second, and third. Some conceptual questions like what does this mean, or what would happen type problems, kind of like the bug on the windshield thing. We'll get to it. And then you might see a question about a force at an angle. So let's just go ahead and roll with it. So here's your review video solution. All right, so our first problem, we have a 405 rightward forces used to drag a large box across the floor at a constant velocity. The coefficient of friction between the floor and the box is 0.795. Determine the mass of the box. Okay, so let's just go through these one thing at a time. What I am going to do is kind of highlight some stuff here first. So we know a 405 rightward force. We know it's moving at a constant velocity. And the coefficient of friction between the box and the floor is 0.795. So the first thing that we should do is draw our free body diagram. So here is the box moving across the floor. We have the normal force. We have the force of gravity pointing straight down. And we have a rightward force. It doesn't tell us what the rightward force is, so we can just say it's, I'll call it a pull. Why not? You could write force applied. Doesn't matter. So there is friction. So remember, friction is going to oppose the direction that this thing wants to go. So it's going to be pointing to the left. And this is moving, so it is kinetic. Every free body diagram needs a coordinate axis. So up and right is positive, left and down is negative. And this will, the acceleration. Okay, so we are moving at a constant velocity. So my acceleration is 0. Awesome, labeled all my forces, got my coordinate axes, and I have done something with, I got my acceleration up there too. So I think we're good to go to move on. So the first thing I do, if you don't know where to start, is to just write Newton's second law, which says, add up the forces, set it equal to ma. So accelerations are not forces. Accelerations are caused by net forces. So don't get those confused. They're both vectors, but acceleration is not a force. That might be a good true-false problem. I don't know. Maybe. But I like it. Okay. So let's see. We got forces going left and right, X direction. We got forces going up and down, Y direction. So let's just go ahead and start with the sum of the forces in the X direction. So I'm going to look at my picture. So the X direction is left and right. So I got the force of the pull, and that's pointing to the right, so it's positive. The last thing I got is the force of kinetic friction. So that is going to be negative because it is pointing to the left. Now I've accounted for all my forces, so I'm going to set it equal to MA. Well, here A is 0, so the right-hand side is equal to 0. Now, one of the equations that you are going to need to know is the equation for the force of friction. And that's going to be equal to the coefficient of friction, which is mu, multiplied by the normal force. So we'll get to that in a second. But let's just go ahead and finish adding up these forces. So we got, in the y direction, I got the normal force up, force of gravity down, so that's minus mg. It is not accelerating in the y direction, so that is also equal to 0. And I'm going to call this equation 1 and equation 2, just so we know which equation we're working with. Okay, cool. So let's see, where do we want to start? Well, I'm going to look at equation number 1 because, we got some numerical values for these things. And so we know we're going to be putting some numbers into this somewhere. So let's go ahead and solve equation number 1 for force of friction. Why not? Force of friction is equal to force of the pole from equation 1. Well, we know the equation for the force of friction. We just wrote it. Put it here in this green square. So let's go ahead and substitute that into here. And I'm going to try to color code these things so that you can kind of keep an idea of where these terms are going and where they're coming from. So let's see. Force of friction is mu times n. So we can write mu times n is equal to F. Cool. So let's see. That was here. So we can follow these green squares here so you can see where this force of friction is going. And now let's see. Well, we want a mass. I don't see an M, but we can find it buried in this normal force term. So if we look at equation number 2, we can solve that for N. So we can add this mg on over here. So we get, from equation 2, wrong color. So from equation 2, we see that N is equal to mg. So let's take this, N is equal to mg, and substitute that on in here for N. So what we are left with is mu mg equals force of the pole. So let's see, green from friction. So there's friction, that's where that came from. And then we also have the mg here from the normal. Hopefully you can follow this color coding scheme. So let's see. We got a mass term now, so let's solve it for it. That's what the question is asking us for. So we get divide by mu g on both sides. So m is equal to F pole over mu g. And here is my final expression. So we go through and we say, well, do I know the force of the pole? Yes, it's 405 newtons. Divided by mu, which we know is 0.795. And g is 9.81 meters per second squared. So what are we left with over here when we do this? We get, let's see, what do we get? I didn't work this one out numerically yet, so let's see. 405, let's see, divided by 0.75, that's not 0.81. 3.2 meters per second, I think. No, let's see, I did that wrong. 51.9. 51.9. This is mass, remember, so it needs units, kilograms. can follow with this color coding thing where these boxes are going. Okay, so that's question number. Question number 2, which of Newton's laws is known as the law of inertia? Well, that one is easy. That is Newton's first law of motion. Remember, an object at rest will remain at rest until acted upon by a net outside force. An object in motion will remain in motion until acted upon by a net outside force. So that is Newton's first law, which he took from Galileo. Newton just had he kind of picked up, Galileo died, but Newton also had a better publicist. So, yes, Newton's first law is the law of inertia. Cool. Well, Newton's third law is also known as the law of action-reaction. So, I'm sitting in the chair is pushing back up. I push down on the table pushes back up. You're pushing down on the floor pushes back up. Bug hits your windshield hits your bug. Equal magnitude force, just opposite directions. That's the third law, sometimes called the action-reaction law. But number 3. All right, so question number 4. A bug hits your windshield while you're driving in your car. The force that your windshield exerts on the bug is blank to the force that the bug exerts on your windshield. Well, we just kind of talked about this. So this is Newton's third law. So the bug hitting your windshield, the force that the bug exerts on your windshield is the same force that your windshield exerts on the bug. Now, I know what you say, well, but Mr. Lehman, the bug goes splat on the windshield. Well, the forces are the same. We can say anything about the masses and the acceleration. So if the forces are both the same, let's take account for the bug, right? The bug has a very small mass. So big acceleration. Your car, very big mass, very small acceleration. The bug hitting your windshield has never knocked you out of cruise control. So Newton's third law, they are going to be equal to. That's the third law. Action-reaction. So what property of matter determines the object's inertia? Well, it can't be the wave function because that's a quantum mechanical distribution of the probability of a location of a subatomic particle that obeys Fermi-Dirac statistics. It can't be the velocity. It's not the acceleration. Well, it's gotta be the mass because remember, inertia is the tendency of an object to resist an acceleration, speed up, turn, slow down, those kind of things. I always use the 2 examples. It's easier to move a shopping cart, an empty shopping cart around because the mass is really small. It's very low inertia, very easy to get up, speed up, slow down, turn. Well, it's that full shopping cart, it's going to be a little harder. Or if you want to go to the extremes, it'd be easier to push me than it would to push a tank, right? Tank's just got a lot more mass. Tank has more inertia than I do. It's a lot harder to speed up or slow down. So what property of matter determines the object's inertia? It is going to be the mass. Awesome. All right, so what net force is required to accelerate a car at a rate of 8.2 meters per second squared if the car has a mass of 2,616 kilograms? Well, this is just a simple Newton's second law problem. You don't need a free body diagram. You don't need anything. Remember, Newton's second law says that the net force is equal to ma. So F is equal to ma. We want what force? So let's see. Force is equal to 8.2 meters per second squared times, let's see, the mass, 2,616 kilograms. And look, forces are vectors, forces are have units of newtons, and we got us a kilogram meters per second squared. That is a newton. So if you are asked, what are the units? How do you decompose a newton? So forces measured in newtons equals mass, which is in kilograms, times acceleration, F equals ma, meters per second squared. So if you were to decompose a Newton, what do you get? Kilogram meters per second squared. That's a good question too. I kind of like that one. See who's actually watching, paying attention to the video. All right. So let's see. All right. So question number 7. During a football game, 2 players are pushing the coach on the sled. The combined mass of the sled and the coach is 300 kilograms. Coefficient of friction between the sled and the grass is 0.8. The sled accelerates at a rate of 0.58 meters per second squared. Determine the force applied to the sled by the players. Okay, so let's see. Let's draw us a free body diagram here. So here's the sled on the surface. There's my force of the push. You can draw it on the left-hand side if you wanted to. Like if you wanted to do, F push like that. That's absolutely fine. Just make sure you know it is still a force, same magnitude. Go to the right. All right, so there's my force of the push. Let's label my mass here. Okay, we got the normal force. We got the force of gravity. Let's see, we need a coordinate axis, X, Y. We also got friction, so that's going to be the force. Now, is this thing moving or is it static? It's moving, so it's kinetic. Friction. Cool, and it will be accelerating to the right. Remember, we use a squiggly arrow for acceleration, not a straight arrow. Why? Because we don't want to think it's force. They're 2 different things. So we probably shouldn't label the same either. Okay. So let's see. What do we got? Let's just do it the same way every single time. So let's write Newton's second law. And it says the sum of the forces is equal to the mass times the acceleration. And let's just add up all the forces in the x direction. So we're looking left and right here. So I got the force of the push minus the force of kinetic friction. And that's going to be equal to, in this case, it is accelerating to the right. How do I know? Free body diagram. Look, there's a squiggly arrow pointing to the right. So that's going to be equal to MA. And let's see. Let's add up the forces in the y direction. So we get the normal force minus the force of gravity. It's pointing down. And that's going to be equal to 0. It is not accelerating up or down. It's only accelerating to the right. So I'll call that equation 1 and equation 2 just in case. So let's solve equation 1 for, what the question is asking us to solve for. So let's solve for the force of the push. That's what we want, right? Cool. So let's solve equation 1 for F push. So we get F push is going to be equal to MA plus force of kinetic friction. Awesome. So we know the force of kinetic friction is equal to mu times N. I'll just keep the color coding here the same as we did in the last one. So that one is going to go right here. And we can write this as F push is equal to MA plus mu times N. Where mu N, that's just my force of friction. The equation for force of friction. And let's see. Well, I don't know what the normal force is, but I can find it in equation number 2. So let's see. From equation 2, we can see that N is equal to mg. I'm just adding the mg over here to the right-hand side. So we get... here's my N. There's my N. N is equal to mg. So this equation... Pen's messing up on me here. Let's see. So my pen... I'm sorry. So my equation is going to be F push is equal to MA plus mu mg. Where here is my normal force. And let's see. Here is my force of friction. Lost my cursor there for a second. Okay. So now we get F push equals ma plus mu mg. If you wanted to, we can simplify this a little bit. You'll get the same answer. You don't have to. It's just always good practice to always simplify your equation. So all I did was factor out an m, right? So if I distributed that, I would get that equation. I'd get the other equation back. So F push is equal to the mass. So this is going to be the mass of the sled. So that's 300 kilograms times the acceleration of 0.58 meters per second squared, plus the coefficient, which is 0.8, and G 9.8. So the force of the push is going to be equal to, let's see, what do we get? We get 2,528.4. newtons. And there is my solution right there. Cool. So it's almost identical to the other one. The only difference is this one is accelerating. The other one was not. Cool. All right, so moving on. Question number 8. A rightward force of 302 newtons is applied to a 28.6 crate to accelerate it across the floor. Coefficient of friction between crate and floor is 0.75. Determine the acceleration of the crate. So we're just like doing the same thing, but we're just solving for different variables. So let's draw our free body diagram. We got our normal force. We got our force of gravity on a surface. There's my rightward force, F pull or F push, it doesn't matter. And let's see, we got coefficient, we got kinetic friction. So remember, you might see, I might have, that's a K. I might put an S. So is it kinetic or is it static? Which one should it be? This one is moving, so it is kinetic. And it is accelerating to the right. Remember, squiggly arrows for accelerations because they are not forces. So let's see. Let's go ahead and write Newton's second law, which says sum the forces, set it equal to ma. So let's start adding up the forces in the x direction. And so let's see, what do we got? We got F bolt minus force of kinetic friction is equal to ma. Why is it ma? Because it is accelerating to the right in the positive direction. So add up the forces in the y direction. We get the normal force minus force of gravity mg is going to be equal to 0. Why? Because it's not accelerating in the y direction. We'll call that 1 and 2. Awesome. Okay, so we want the acceleration of the crate. So we can solve for A from equation 1. So I get A is equal to force of the pull minus force of kinetic friction all over M. Cool. I don't know the force of kinetic friction outright with numerically, but we do know an equation for it. That's equal to mu times N. So let's take that and we'll put that in there. I won't do the color coding anymore. I think you understand what we're doing. So acceleration is equal to the force of the pull minus mu N all over mass. Cool. Well, I don't know a number for N, so well, we know an equation for it. We look at number 2, we can see that N is equal to mg. You can solve this or you can simplify it. I like to simplify, so F pull over M minus mu G. Why is it minus mu G? Because these M's cancel. Cool, so we get, let's see, acceleration is equal to a rightward force, so 300 100, and 2 newtons divided by the mass, 28.6 kilograms. Oh, look, we're left with a meter per second. Awesome. So minus 0.75 as the coefficient of friction. 0.75 times g, 9 meters per second squared. So here we get acceleration is going to be equal to, let's see, what do we get? 3.2 meters per second squared. So, just remember, we got the force of friction there. There's the force of friction. There's from the force of friction. There's your force of friction. What about my normal force? Well, normal force is mg here, and we got the normal force from solving equation number 2 for the normal force. So that's where these terms came from, if you were wondering. So n equals mg from equation 2. So let's see, that is going to be there. And yeah, that's about it. So there's my normal force. So you can see normal force n is equal to mg. Awesome. It should be getting pretty easy for you at this time because we have had plenty of practice. We've done this for several weeks now, so should be coming pretty intuitively to you. Okay, number 9. Let's see, we are almost done here. Free body diagrams are tools that we use to help us set up Newton's second law problems. Absolutely. 100%. What is the mass of a falling rock if it produces a force of 147 newtons? All right, well, this is just another simple F equals ma thing. So let's see, F equals ma. What is the mass? So we want to solve for mass. So m is equal to force over acceleration. Force of 147 newtons divided by the acceleration. Well, if it's falling, it's here on Earth. The acceleration is 9.81 meters per second squared for an object that is in free fall. So let's see. Where was that question? 27.3. I'm sorry, 14.9. 14.9. Let's look at 0.9. So that's just a simple F equals ma. And I know that is question 10, but I wrote a couple more here for you. So a box being pulled to the right along a frictionless surface. Choose the free body diagram. Okay, so a box being pulled to the right along a frictionless surface. So there's going to be, it's being pulled to the right, so there's got to be a tension force to the right. Frictionless, so there's nothing to the left. There's no force balancing the force of this pull, meaning there's no frictional forces. It says frictionless, so there's nothing opposing that, so there's going to be a net force to the right. So I know that my free body diagram must have an arrow, tension, T1, vector pointing to the right, and a squiggly arrow for the acceleration also pointing to the right, because objects will accelerate in the direction of the net force, and to the right is the direction of the net force in this case. So we're also going to have the normal force up and force of gravity down, but they're canceling each other out. So let's see. Let's go through these. So let's see. Oh, we got a T1 pointing to the left. That can't be it. We do have a squiggly arrow to the right. All of our forces are vectors. And we do have coordinate axes, but it can't be A because T1's pointing to the left. All right, well, what about B? We got a T1 pointing to the right, which is fine. We got an acceleration as a straight arrow to the right. No, we don't use straight arrows for acceleration. We use squiggly arrows for acceleration because accelerations and forces are not the same thing, and we don't want you to get confused when looking at your free body diagrams. Also, there is no coordinate axes on B, and these forces that are labeled do not have arrows over them. These are vectors. Need arrows. Signify that they're vectors. It can't be B for those reasons. No arrows over the vectors and no squiggly arrow for A. Well, I guess the only thing is C, but let's verify it. So we got a T1 vector pointing to the right. We got a squiggly arrow for the acceleration pointing to the right. We got us a well-defined coordinate axes. I like it. Normal force vector up, force of gravity vector down. Awesome. So your answer is C. So expect to see a problem kind of like this. Do you have an idea of what I'm looking for? Look for the arrows over the vectors. Squiggly line for acceleration. Make sure that the forces are pointing in the right way. So who knows what you might see? But it would be those are the things that, kind of some of the things that I want you to be looking for. Okay, and lastly, you may or may not see a box pulled to the right by a rope, so some force at an angle. So let's just do this one. I'm not going to give you any numbers. I know, and you hate that, but I don't care. All right. So let's go ahead and just, see what we got. Well, let's just draw our free body diagram here. We got our normal force up. We got our force of gravity down. And let's say, since I made up this problem, I'm just going to say it's frictionless. So that's what we'll go with. So let's see. We will be accelerating to the right. We need a coordinate axes, X and Y. That shows us what's positive and negative. So before you get started with Newton's second law, if you're not good at this vector decomposition thing, remember breaking a vector into its X and Y components, then I suggest you do this step every single time. And what do I mean is let's just redraw this arrow. So here's my T. Remember when we kind of did this in 2D kinematics? How fast is it going in the X? How fast is it going in the Y? So here's your tension vector, and it is at some angle. So there's T1X, there's T1Y, there's my angle theta. So let's do this. Let's go. T1X is going to be in red, and T1Y is going to be green here. Okay. So where do we go from here? Well, kind of business as usual, right? So let's just add up. Let's do what Newton's second law tells us to do. Add up the forces, set them equal to MA. Well, we got both X and Y directions here, so we're going to have to do the sum of the forces in the X direction. So I look at my free body diagram, and I have, let's see, there's T1X, right? So T1X is pointing that way, T1Y is pointing up. Now, on your free body diagrams, do not put these vector components, especially if you take the AP exam later on, AP Physics. They will take off points if you decompose your vector in your free body diagram. They want you to draw it again. But for this class, I don't care. I get what you're doing. All right. So let's see. We have T1X pointing to the right. So it's positive. Do I have anything else pointing to the right? No. So when we have accounted for all of our vectors, we set it equal to MA. Is it accelerating in that direction? Yes. Positive X direction. So that's equal to MA. That'll be equation 1. All right, so now let's go ahead and add up all the forces acting in the Y direction. So let's see, we got a couple things going on here. We have T1Y, that's pointing up, so positive. We also have a normal force plus the normal force minus the force of gravity. And that's going to be equal to 0. It is not accelerating in the Y direction. Free body diagram, arrows pointing to the right. Cool. So let's do some vector decomposition here. So T1x. Well, this leg of the triangle is adjacent to my reference angle, so that gets cosine. So this is going to be T1 cosine theta. And in the Y direction, that is opposite my reference angle, so it is going to get sine. So T1 sine theta. Now, technically, this is the magnitude here, but it's got to be positive. Anyway, so I'm just putting T1. If you wanted to put the, this thing on it, you can. So technically, it's magnitude, but it's just some numerical value. And now, let's go ahead and substitute these colors into equations 1 and 2. So for equation 1, we get T1 cosine theta is equal to MA. And so we'll call that equation 3. So then equation 4, let's just substitute this T1y value here. So you get T1 sine theta plus the normal force minus the force of gravity. That's equal to 0. We'll call that equation 4. So now there's a bunch of things you can do here. Several things I can ask you. Well, what do we want to solve for? I didn't give you any numbers or anything like that. So let's just symbolically, I don't know, let's solve for the acceleration, but I didn't give you a value for T1, right? So how could we do that? Well, I could do a systems of equations or a substitution to eliminate a variable. So let's see. If we want the acceleration, so acceleration is going to be equal to T1 cosine theta over M. Well, if I didn't give you T1, well, we can eliminate it by solving equation number 4, this one right here, for T1. So let's see, T1. Let's add everything over so you get T1 sine theta is equal to mg minus the normal force. So T1 is going to equal to mg minus the normal force all over sine theta. So then if you really were inclined to, you could take this and stick it in there. And then you can put some numbers in. Would I give you something that complicated? Probably not. But here I just wanted you to see the vector decomposition, breaking it down, x and y components, where they go, and how we put them back into our systems of equations. And once we have our systems of equations, we can solve for pretty much whatever. So since I didn't give you numbers on this one, that's just it. So like we would take this T1 here. Let's just finish this. I like finishing problems. So let's see. Acceleration is equal to mg minus n over sine theta. That's an N right here, not an H. So we get cosine theta and then you can do some simplification here if you wanted to, but you'd get the same answer. So this is just an idea. But would I give you something this tricky? Probably not. But I just wanted you to see, like, you know, what a medium level problem, medium-ish level problem might look like. So with that, that finishes the test review. So I hope this has helped, and you know, you got 5 attempts at the review, so you know, like, do one, wait a little while, do it again, work it all out. Try and solve for other variables, manipulate those equations around. What if I gave you a numerical value for the first function? Practice the things we've done in class. Look up videos on YouTube. Look up practice problems on Google. There are tons of them. Just Newton's second law problems. Awesome. The more you practice, the better you're going to get. So your confidence will go up. When your confidence goes up, you're building that intuition. So when you trust your intuition, you can think through these problems without having to do step by step every single time. So your speed goes up, your confidence goes up, your speed goes up, your scores are going to go up. And I know everybody's going to kill it on their test next week. So I hope this helps, and I will